So the greedy algorithm is just your basic lowest level of algorithm that any 2-year-old would know. You the 2-year-old comes into a room, sees objects, and grabs the ones that feel the best, and makes an irrevocable decision about taking them, without worrying about the future ramifications. And most computational problems cannot be solved by a greedy algorithm, but a few of them can. And even for the problems that can't be solved by a greedy algorithm, sometimes the greedy algorithm will give a good enough solution, or maybe minimally, you should understand why the greedy algorithm doesn't work. So one example of an algorithm that doesn't work is the input's a graph, and the decisions that need to be made. Right, a solution is a decision, is a sequence of decisions, right? What edge should we take first? What edge should we take second? And so forth. And the greedy algorithm is the algorithm that just takes the edge that feels locally to be the best, right? This edge here is heading towards T and it's cheap. Let's take it. But you'll see the optimal solution is over here. And so the greedy algorithm fails to find the optimal. General optimization problems is you have an input that has some exponentially large set of possible solutions. For each solution, you can compute the cost, and the goal is to find a valid solution with optimal cost, right? Either it's a minimization or a maximization. And for greedy algorithm, the instances tend to be objects, and the solution is maybe a subset of those objects, or a decision made about each object. And the solution is valid. Some subsets of some solutions aren't valid because of maybe conflict between the objects or something, right? So, and then the cost of the solution might be the number of objects taken, or the sum of the cost of the objects, or the solution might, the cost might be something more complicated. We usually use cost when we're trying to minimize it, and value when we're trying to maximize it, but it's the same idea. All right, and our goal is to find an optimal, valid, sort of non-conflicting solution. Optimal means it's a solution that's better than any other possible valid solution. The brute force algorithm, of course, is exponential time. It tries every possible solution, and there are too many of them. So a greedy algorithm looks at the object that looks somehow the best and commits to it. And for example, if there's a party tonight, you might choose to go to it, even though not studying for your exam tomorrow might be a bad plan. So that's the difference between a locally greedy choice versus that might have long-term global consequences versus being globally optimal. We saw this sort of example before where we have some number of prizes, and the greedy algorithm starts grabbing the lion because it looks really cool, but there are consequences if you take the lion. Like you can't take the zebras, you can't take the elephant because the lion will eat it. Not to mention your mother might not be too pleased with you bringing a lion home. But as I said, the greedy algorithms don't try to predict the future. And if there's a mistake, they don't backtrack because that would be too time consuming. So the algorithm sort of sorts the objects based on how good they are, and then goes through them in that order, and will accept it unless there's a good reason not to, right? It makes some decision based that maybe it doesn't accept it because you can't, if it conflicts with objects already taken, like you can't take the elephant if you've already taken the lion, or maybe it'll reject the next object because it doesn't fill any new requirements that are needed. You can think about this algorithm recursively, where you commit to that first object and then you recurse on the rest of the input. We're going to do that when we're doing recursive backtracking, but not here. Let's talk about the general sort of layout of a greedy algorithm. There's a greedy criteria, which the algorithm doesn't know what, we're going to assume that the algorithm doesn't know what the objects are in the input. Before seeing the objects of the input, it's going to assign every possible object that it might ever see some real number. That's the greedy criteria. And then the objects will receive the objects from the input in this order. And then the algorithm, when it receives the next object, must make some sort of choice, and it does that knowing the past decisions, past objects, but not knowing the future objects. And when it makes that choice, it's an irrevocable choice about that object. Why are these algorithms so restrictive? Two basic reasons. The one is it makes them very fast, and also, like in 2011, when we looked at stacks and heaps, by restricting what the data structure can do, one, it makes implementing it really fast, and two, it gives heads up to anybody studying the algorithm, the data structure, as to what it's allowed to do and what it's not allowed to do. So let's do a concrete example here, where the problem is to find the minimum number of coins to make up some given amount. So here we have an infinite number of quarters, dimes, nickels, and pennies, and we need to make up some 92 cents. And so think about these as objects, and the 92 cents as being a relationship between them, because a solution is a subset of the coins that has to add up to 92 cents. So if the coins don't add up to 92 cents, then in some ways they conflict with each other, right? The cost of a solution will be the minimum number of coins in your solution, and the cost of a solution is the number of coins in the solution, and your goal is to minimize that. So here, what is the obvious greedy algorithm? Well, it's going to sort the coins based on how good they seem. The greedy criteria is going to grab the quarters, consider the quarters first. Why? Because they make as much progress towards the 92 cents without, with only using one coin, right? So it's going to first consider the coins, and what the choice will be is that it will keep taking the coin as long as it doesn't exceed the 92 cents. So here the algorithm first takes the quarter, takes the next quarter, takes the next quarter, doesn't take the fourth quarter because it adds up to too much, and then considers dimes in the same sort of way, and right, takes a nickel, but the nickel takes 2 pennies and is done, right? So this is the solution, which is has 7 coins, and you probably would believe that this is optimal. In fact, this algorithm um, always returns the optimal solution. Now, before you get too casual about this, let's consider another example in which you're in a country that has coins which are 4, 3, and 1s, and you're trying to make up 6 cents. So the greedy algorithm is going to start by grabbing the 4-cent coin, but we see that's a mistake because once grabbing the 4, can't take a 3, so has to take the 1 and the 1, which makes up a solution with 3 coins, where if the algorithm had been more creative, it could have taken 2 3s, which would have only been 2 coins. So this is an example where the greedy algorithm fails. And in fact, this kind of problem is kind of like bin packing or knapsack problem, where you have a bin of size 6 and you're trying to pack in these objects of size 4, 1 and 1 and 3, and that problem is shown to be NP complete, meaning if you had an algorithm for it, then our whole cryptography world would collapse.